Alright, what I'd like to next do is the section 4.3.4 in our book called Hazard Function, Reliability Function, and Failure Rate. This is a pause from the continuous distributions, and there's a very specific reason for it. Okay, so we're defining R of t as a new function. Okay, however, it's simply the complement of the CDF, and it's known as the reliability rate or reliability function. Our book doesn't say this, but more commonly I've heard it referred to as the survival function. And again, it's just the complement of the CDF. Okay, so the longer the timeout you get, then the less likely you're going to have of survival or reliability. Okay, that's the intuition behind it. So it's very simple, and even more frequently used than that is what's called the hazard function. Okay, in the hazard function, little h of t is the PDF divided by the reliability or the survival function. Okay, and that looks interesting. There's an exercise that I'd like you to go ahead and give a shot at, which is to take this relationship right here, definition of hazard function, and prove that the PDF is equal to this expression here in terms of the hazard function. And I'm just going to give you a hint. You want to make use of this fact here, which is the hazard function is h of t is minus the natural log of the survival function. Okay, so if you take that and work with it, then you can find this result. Okay, now I like this. It's saying give us an intuition for the hazard function. So we think differentially, and if we're on some interval of time, let's take a small amount of time, t plus dt. Okay, so some small interval. Then we can think of h of t dt as f of t over 1 minus big F of t dt being approximately the probability that our event t occurs in that small interval. Okay, given that it occurs past time t. Okay, so it's like an instantaneous rate of occurrence. You could think of it like that. As such, we can use this differential notation. Probability that big T occurs inside the interval here, divided by dt, and take the limit as dt goes to 0. Okay, that would be the instantaneous rate of death or rate of failure, or again, just the thing occurring, given that it's survived up to that time. All right. Keeping in mind it's a rate, not a probability. That's something to keep in mind. And there's a little typo in the book here, but the failure rate for an exponential random variable turns out to be lambda. Okay, and that captures the memoryless property right there, because the failure rate stays constant over time. Very interesting. Okay, so now what's the big deal with that? Okay, the big deal with that is that the gamma hazard function is not in a closed form. Okay, but when you are an engineer dealing with quality control or lifetime of components, you kind of want a closed form function. So we start with this hazard function here, which is it turns out to be a well-behaved hazard function. You can see that it's in the form of a power, okay? And if alpha is bigger than 1, then it's monotonically increasing, okay? If alpha is equal to 1, then you can see that this t term goes out and we just have 1 over beta. Okay, so that's fixed. And then when alpha goes less than 1, then, let's see, alpha goes less than 1. Okay, then it changes its behavior the other direction. And let me try to hit that in our notes. Okay, what's going to turn out to happen is we're going to derive using the PDF relationship to hazard function a new random variable, and it's going to be called the Weibull random variable. This was developed in the early 1900s, popularized by a Swedish engineer named Weibull. Okay, and so alpha less than 1 is a failure rate decrease over time, greater than 1, failure rate increase over time. We'll look at these graphs. So we have their relationship mapped out right here. Okay, good. Now, I'm not going to do that derivation, but it's in that formula that I stated. And so let's move into the graph. Okay, so I'm going to show 3 graphs here. This is alpha less than 1, so we have steeper than an ordinary exponential. Okay, so the failure rate is decreasing over time, and just check myself. That's going to refer to maybe a high infant mortality. A lot of the babies die early, but then the fit survive, and you could use that for parts as well. All the lemons break, and then the other ones keep lasting a long time. Okay, so the failure rate goes down. On the other hand, if the failure rate increases with time, which would be a standard process, as we age, we become more likely to die. Same on with manufactured parts, then that's an alpha greater than 1. And that alpha equals 1 case is going to get you, plug in 1, 1, 1, 1, you're going to come up with, there's a 1 over beta. That 1 over beta would equal lambda. The exponential random variable. So the Weibull is another alternative generalization of the exponential random variable as well. Its moment generating function is complicated but can be obtained with variance and expectation. Also a little more complicated. So that just turns out to be how it is. For our next probability distribution, we're going to consider the beta distribution. Now, the beta is a little bit different than the others. The last 3 we've looked at all start at 0 and then have no upper bound on their support, whereas the beta is bounded like the uniform. And in the book, they give A to B. Frankly, I want to speak of our beta as just bounded from 0 to 1. This is how it's defaulted in so many places. R, it's defaulted here. In fact, it doesn't even have the option for A to big B. So when you look at this PDF for the guy, then if you convert A to 0 and B to 1, we're going to get something like this. We're going to have gamma alpha plus beta all over gamma alpha, gamma beta. Don't get confused with that, times, now the A is 0, so we just have x to the alpha minus 1, and the B is 1, so I'm just going to have 1 minus x to the beta minus 1. Okay, that's a lot cleaner. Now, if you'll recall, for the random variable, let's just call it y. Let's say y follows a binomial random variable, or a binomial distribution with parameters n and p. That probability that y equals y turned out to be n choose y, and we used pi, didn't we? So let's call it pi. Pi to the y, 1 minus pi, to the n minus y. And we argued that this is a valid PMF. Okay? Now, just by extension, you can visibly see that the beta, in a sense, is a continuous analog to the binomial. Okay, so if we're trying to consider how this guy actually is going to integrate to 1, then we can see it here. X is bounded 0 to 1. Okay, so we have x to the alpha minus 1. That corresponds with this guy here. Okay, and we're going to have, well, I should say this whole term. Let me clear that. Okay, this whole term. 1 minus pi, that's fixed here, whereas here it's going to vary, but again, x is 0 to 1. So once x is fixed, then it's fixed. Okay, beta and alpha then are also going to be fixed. And so as you take the integral from 0 to 1, then it turns out that this guy's 1. Okay, so you have the analogous probability part here. Okay, what's up with the minus 1? There's something a little bit alarming from that. Keep in mind this is n choose y, but that special feature of gamma is that gamma of n is equal to factorial n minus 1. Okay, so there's a minus 1 here. So you've got 2 less on the top part, you've got 1 less on the bottom part, so that's where these 1s are going out, and this gives you the analog of the combination. So just a little heuristic kind of hand waving there, but we can be convinced that, yeah, it's a valid PDF. I'm not sure about its moment generating function. I haven't researched it in detail, but my basic books do not include one. And variance and expected value are given. Again, these are going to wipe out under the 0-1 assumption, so everything kind of cleans up there. All right, now what's its application? Well, a lot of times it's used to model probabilities. It's a super flexible distribution, and I want to show you some of it on R. Again, exact same form as we've been doing here, so I'm plotting 3 different y-axes for beta, and then I'm going to plot them. That's it. Boom. Okay. The parameterization I used here, first component is alpha, second is beta, and when they are equal to 1, both equal to 1, you get boom. It reduces to the uniform distribution. Can we see that? Let's take a look. Let's go to this form here. 1, that's going to boom, become 0 in the exponent becomes 1. 0 in the exponent becomes 1. So that goes out. And all that we're left with here, let's see, we have, so that's gamma of 2 over gamma 1, gamma 1. All right, so that's going to be 1. And in fact, 1 is the PDF for the uniform. F of x equals 1. When you integrate it from 0 to 1, you get 1. Okay, wow, interesting. It's cumulative, going to turn out to be x. Okay, so it does actually achieve that reduction. Awesome. Okay, 2, 2, you get this type of shape. So interesting. Notice we're at 0 here. Okay, I should put density instead of probability. That would be better. Density. And when you have less than 1, then we're going to get this U shape, which is really interesting. In a sense, there's an exponential on the left and an exponential on the right. Area under the curve is always 1. What happens if the parameters are not the same? Then I've done a couple of them. Okay, well I did a 3, 3, but you notice an exponential type shape. So it's a very flexible distribution. Now, we're going to move to the grand finale, which is the normal distribution. Okay, the normal is amazing, and we'll talk about it a lot in class. It's called the normal because it's the benchmark. No other distribution gets the benchmark name. They're all weighed against it. And you'll notice it has 2 parameters, mu and sigma. Okay, mu is the mean, and sigma is the standard deviation. Standard deviation. I've avoided naming the other parameters with great length. Some lambda is a rate parameter. Okay, you have that. Alpha is a shape parameter, although it depends upon which distribution as to exactly what that means. But the other distributions don't have mu and sigma typically as their parameterization, but those are the natural things we think of things in terms of. And again, that's why this is called the normal distribution. Okay, x is the limit of the binomial distribution. That's where it's derived from, and I think I'll make an argument about this in class, but I will just say that if you have, in fact that's how it was originally derived, you'll have some type of binomial case like this, and once you take more and more observations, so as n gets larger, then we're going to have finer and finer numbers of bars. If you could just kind of humor me here and let me do an easy sketch. So you get more and more bars, and it just turns out that when that happens, you get a bell shape. It just happens. It's amazing, and we can easily demonstrate this on the computer. It's very, very cool. And this turns out to be the density that makes that happen. Okay, it's got a 1 over square root pi, which is really, really interesting. And it's e to this power. Its kernel there is e to the minus x squared, which does not have a closed form. That's another interesting feature of it. But the bottom line is, this is the classic bell-shaped curve, which we will speak much of. When you look at it in R, you can pull it around. I'm going to demo 3 of them here. Whoa, what happened? Okay. There it is. I've centered them, so the red one is centered at 0.5. Oh, I've mislabeled. Blue one centered at 0.5, 7.5. Red one centered here at 0 with standard deviation 1. Green one centered at negative 0.5 and standard deviation 1.5. So you can expand, contract, slide them around. Everything is fine. And that covers the basics of that one. I wanted to do one more R demonstration and then close this segment out. Let's take a look at the notes here. Demonstration of R's probability functionality. Okay, up to this point, if you look through these scripts, we've been sticking the D on the front. That gives probability density. Okay, if you take the same command, whether it's norm or binom or gamma, then you put a P in the front, it gives you the cumulative distribution function. We saw some of those in the discrete presentation. If you put Q in front, it gives you the quantile. Recall, quantile is just percentile divided by 100. And if you put R in front, it gives you random numbers drawn from that distribution. And I want to just give a simple demonstration here. So we're looking at the graph of the normal, that's fine. If I want the probability that x is bigger than 10 from a normal distribution with mean 5 and standard deviation 10, then P norm is going to be less than or equal to 10. It's defaulted as the proper cumulative distribution. So I'm going to go 1 minus, and I just run it, and boom, that gives me the probability. Okay, so done. Do I have a graph of that guy? I didn't have one set, but that's okay. If you want to know what's the probability that x is from -20 to 15, in fact, I'll hit those. Let me go ahead and jump down here to 5. I'm just going to run this and then I'll come back. Okay, the blue is the random variable that I'm thinking about. So the probability that we are over 10, so here's 10 right here, that turns out to be that 31%. So you can see, yeah, that by eyeball, we'll buy it. Number 2, -20 to 15. Okay, so -20 is going to be down here all the way to 15. That looks like it's a fair bit. So we're going to do the 15, that's here, and it goes left, everything left. And we're going to just take off the -20, which is this little component here on the left. So if I were to write it out, then it looks like this. Okay, so here's 15, and here's the -20. So we start off by taking the whole region, and then we subtract off this region here, and that will give me the desired region in the middle. Okay, so I'm just using 2 commands to obtain that. Boom. 83%, as we said, it should be high. Now the quantile command is in reverse. So what if we want, what's the value on the x-axis that gives me 95% of the area? So I've now changed from P in the first position to Q. Run it, boom, 21. So right here at 21.45, that's the 95th percentile, or the 0.95 quantile. Okay, change the Q into an R, and that allows me to generate random values. So if I run that, boom, I get 19 observations randomly drawn from this distribution. Now, there's a sophistication here that I want you to see. If it's a uniform distribution, that is just a rectangle, okay, then every observation is equally likely to occur. That's not the case with our bell curve. It's more likely to be near the mean, which is 5, and close to 5, than it is to be out in the tail. Okay, so if you look at these values, then that's what is going to happen when you sample. And to demonstrate this, I'm going to sample 1,000 observations from that, and we'll call that out. Then we'll make a histogram of that. Okay, boom, here's the histogram. And sure enough, most of the values are in the middle, and then we have some farther away. Now I'm going to superimpose the normal distribution on, and when I do that, I'm using my last prefix, D. D gives us the density. So back to the map. Okay, when I use D, D is going to give me the specific value on the axis. P is going to give me the area, which is this whole area here. Q is going to give me the value on the x-axis here, R is going to give a random observation to pop out. So that's how the 4 different prefixes are related to each other and work out. You've got the scripts. Good to go. See you in class. Lord bless you.